Welcome to the EE Smarts lesson, Energy Roller Coaster. Watch the video, think about what you see. Have you ever been on a roller coaster? What does it feel like? Think about the last time you were on a roller coaster. What happened to the car as it climbed towards the top of that first hill? You might remember the car slowed down and got slower and slower as it came towards the top. What happened to the car when it actually reached the top of the hill? Well, it stopped momentarily when it reached that very crest of the first hill. What happened to the car as it rolled over the crest of the first hill? Well, the car then swooped down at breakneck speed as it rolled over the crest and down that first long slope. Potential energy is stored energy, and kinetic energy is energy in motion, or energy of motion. On a roller coaster, when is the potential energy the greatest? Well, when the car reaches the crest of that first hill and almost comes to a stop just before rolling downward, that's when potential energy is at its greatest. When is the kinetic energy the greatest in a roller coaster? Well, when the car has now come over the crest, barreled down that first hill, when it reaches the bottom of the very first hill, when it's moving at its fastest speed, that's when the kinetic energy is the greatest on a roller coaster. Look at the two pictures of the roller coasters. Which one shows greater potential energy? Well, the picture on the left shows greater potential energy because the car is right at the top of that first hill, right before it makes its descent. So therefore, the other picture shows greater kinetic energy. That picture shows the car moving down that first large hill. So potential energy is being transformed into kinetic energy as it goes down that hill. The kinetic energy will actually be at its greatest when the car reaches the bottom of the first hill, when it's at its fastest speed of the entire ride. Now I'm going to do an activity for you. And the materials needed are string, tape, and washers of different sizes. I'm going to set up two tests. For the first test, I will change the length of the string, but keep the washer the same. What do you think will happen to the number of oscillations, that's a complete back and forth of a swing, in 15 seconds as the length of the string is increased? Will there be more oscillations? Will there be less? Will it be the same? For the second test, I'll change the size of the washer, but keep the length of the string the same. What do you think will happen to the number of oscillations in 15 seconds this time as the size of the washer is increased? Will there be more? Will there be less? Or will there be the same? Let's test it and find out.
For these activities, I have the following materials. I have string, tape, and washers, and I have different size washers. For this first activity, however, the washers are all the same size because that is one thing that I'm keeping constant. The length of the string, however, is different for all three because that is the variable that's being tested. So when you see these washers hanging from a string like this, they're making a model like a pendulum because they can swing freely, like a pendulum can. All right, I'm going to move these two to the side for a moment, or to the top here, and demonstrate to you how this is going to work. I'm going to hold the washer even with the countertop, and I'm going to release it. And when I release it, I'm also setting a timer for 15 seconds. And I'm going to count the number of complete oscillations that it can do in that time period. So for a complete oscillation is a forward and back. So here we go. This would be 1. That's 1. So every time it comes to me, 1, 2, 3, 4. You get the idea? That's how we're going to test them. Now, what do you think is going to happen with the 3 different length strings? Will the number of oscillations be the same? Will they be different? Will it get more oscillations as the string gets longer, or will there be less oscillations as the string gets longer? We're going to test it and find out. So here we go. I'm going to set this and set a timer at the same time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right, 14 complete oscillations. Now I'm going to do that test 2 more times when I'm off camera so that we have 3 trials that I'll then make an average of for to help with accuracy, because there's always human error involved and things don't always go exactly as you would like them to. All right, so here we go with the second side, the second length string, the 45 centimeters. I'm going to do the same thing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so that was 11 that time. Now I'm going to do a third one with the longest string. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so that did 9 complete oscillations in that 15 seconds. So as you saw, the frequency or the number of oscillations in a given time actually goes down as the length of the string gets longer. Now we're going to look at and do a test of 3 different size washers, but all the same length string. Okay, so we have a small, a medium, and a large. And I'm going to start with the small one and do the same thing. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. All right, that was 13 and a half because it was halfway through that 13th oscillation when the bell went off, when the timer went off. Here's the next size. Ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Again, 13 and a half. And then the final one. Here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Again, we had just about 13, 13 and a half. So the size of the washer didn't make a difference. Did that surprise you? Well, let's talk about this in a few minutes. In the meantime, I'm going to do 2 more trials for each one so that we have a more solid data table.
Look at the data in the table. Do you see any patterns? You may notice that when testing different lengths of string, as the length of the string increased, the number of oscillations decreased. Were you surprised by that? Why do you think this happened? You may notice that when testing the different size washers, as the washer size increased, the number of oscillations remained the same. Were you surprised by this? Now let's look at the graph of the data. You can clearly see the decrease in the number of oscillations as the string length is increased. Why is this? Well, think about it. The force acting on the washer is gravity, which is constant. When the string is longer, the washer has to fall farther, traveling a longer distance, taking more time. The time it takes for the washer to make one complete oscillation, or back and forth, is called the period. And the number of oscillations in a given time is the frequency. So as the string gets longer, the distance the washer falls is greater and the period is longer. That means that there are fewer oscillations in a given time. In other words, the frequency is less. When using the same length of string but 3 different size washers, you can see that there was no significant difference in the number of oscillations. Why is this? Again, the force acting on the washers is gravity, which is constant no matter the size of the mass. With the strings of all the same length, each washer has the same distance to fall, and therefore a complete oscillation has the same length period. As a result, the same or almost the same number of oscillations takes place for each size washer in the same time frame. Think back to the roller coaster. Do you remember when the potential energy was the greatest? Do you remember when the kinetic energy was the greatest? Now look at the diagram of the table with the washer swinging from it. Where is the potential energy the greatest? The answer is at point A. Just as the roller coaster had the greatest potential energy as it reached the crest of the first hill, the washer has the greatest potential energy just before it is released. That potential energy then transforms into kinetic energy as it falls. Where in the diagram is the kinetic energy the greatest? The answer is at point C. Just as the roller coaster had the greatest kinetic energy as it began its descent of the first hill and it reached that the lowest point when it was going at its fastest, the washer demonstrates the most kinetic energy as it reaches that point at its lowest point when it is going its fastest. So this is the lesson on energy roller coaster from EE Smarts. Thank you for going through it with me.